Um, Welcome to the another problem session. Today is going to be problem session. We've done a lot of concepts, but we're going to discuss concepts here as well. All right, so we're doing MCAT. Let's see, MCAT or engineering. So this is a medical admission test, and this is engineering admission test, and they kind of overlap quite a bit. If you have this much knowledge of physics, you should be okay. All right. Here is this is what we have done. You can find in previous videos. So this problem is called inclined plane, but this is fixed. So there's only one body that can move or slide, So this is one problem we have done. Very classic. You should know in and outs of that problem. Second problem we've done is maybe there's a book here and there's another book here and this is a table. So there are three systems here. This one is fixed and both of them could move. Okay, we have really not done that. I wanted to do it and maybe we'll do it today. Okay. And then we want to do it this problem, very classic, this problem. So this is problem number 3. This also going to be today. I just forgot. Just remember that I meant to do it, but I didn't get time to it. Let's do this one out right away and come back to this. So I will try to do it very quickly. Okay. So this is the table, and this is say M1, M2, and we're saying that there is a force on the M1, and I'm just going to call it F1, and there is going to be frictional force here, and if this is not sliding past this, then it's going to be backward like that. Is going to be this going to be Fs static if not sliding, or kinetic, which you're labeling Fk if sliding. We write sometimes Fk equals to mu k times Fn, whatever the normal force is between these two guys, and we write Fs if it's a max value, may not be the max value, but it's max value, then we write mu s Fn. Not equal to Fs other than max. Okay, so let's work out here. And then there's a same situation here. So this surface can have static friction either direction, or kinetic friction if it moves in that direction. Then if V of 2 is V of 2 with respect to V1, V of 2 with respect to V1, V can move. This is misleading. This can move but with respect to 1. So this M2 can move with respect to this, but if they're not sliding with respect to each other, then it still be static. But only sliding So it's F2 if M2 sliding on M1. So that's the friction picture. So let's see. One of the questions was, so there will be different mu s. Let's go mu s prime, mu k prime here. And let's see this slides much later than this slides situation. So we are going to do mu s mu s prime is greater than mu s case. We're going to do that case. So what can we do? All right. So there are a couple of things you can do to which will depend on the question asked. You might be willing to do. One is think of this guy as one system. Think of this as another system, or think of these two together as one system. So let's see, two together. That's probably the easiest one, looking at a bigger picture, right? So you have M, doesn't matter what's going inside, this M2, this M1. So outside forces, let's use different ink. You have F1. And now this system, if you think of this, its mass is M1 plus M2. You don't worry about what's inside. Like if you're looking motion of a car, you're not looking at inside the car, all the different things that may be moving. You're just looking at center of mass and this one. So it's going to be gravity down will be capital Mg, and so there will be a normal black ink, normal going up, and so this is pushing, and if it's not moving, so there will be a static fraction if not sliding, or Fk if sliding. So you can see Fs will match F1 up to a point. So this Fs max will be mu s Fn, but this one will always be mu k Fn. Let's write down the equations we're going to get. So if we do a free body diagram, so this is the x and y. So you can see F1, all the free body diagram, you write force starting from the origin, Fn, capital Mg. It's going to be Fs or Fk. Just leave it alone for now. Let's call this just F. All right, so, and if there's acceleration, it can be in that direction. If it's moving, then this is very easy to write and conclude all the things that we want to conclude. So everything along the axis, so along x-axis you have a F1 minus F equal to 0, mass times A. So A is just A0, Z component will be 0, so we're just ignoring Z. In the y direction, it's just going to be Fn mg equal to this is 0, so this is big M 0. Now So case 1, not sliding. That just means A equal to 0. This one is regardless of not sliding. So that's the case. So this just means Fn is mg in all cases. But Fs itself is less than equal to Fs max. So I might not be able to write like that. So F not sliding up to this point, Fs max, this maximum thing that is 0. So let me write some. Not sliding in general is F1 minus F is not sliding, so this F will be S equal to 0. So whatever F1 is going to be matched by Fs. But if I keep increasing, suppose if I keep applying greater and greater force, then F1 eventually Fs will reach Fx max, and so at that point this can be written as mu as Fn, and Fn can be substituted over here, mu s mg. So F1 at that point will equal to mu s mg. So they will have to be balanced like that if not sliding. So let's see now, suppose sliding. So up to this point, so F1 0 all the way to less than this, maybe less than or equal to that. Just put less mu s mg, it will not slide. So now it starts sliding. Then you don't need all the way to F1. If it's sliding, you can let it go and it will continue to slide. Okay. So say mu s is 0.3 and m is 10 kilogram and g is 10. Then this says 0 F1 up to 30 Newton. If you multiply these guys, you get 30 Newton. Up to 30 Newton, it will not slide. How about once I get over 30 Newton, say I have a 40 Newton, then it will slide. So, but the questions will, these two equations will be the same, except that now F is 40 Newton. So F is 40 Newton, F1 is 40 Newton, but Fs are not applicable anymore. F is Fk now, which is mu k Fn. And so let's say pick a mu k. Mu k will be less than that. Mu k says 0.1. So this will be so friction force, not F1. F1 is 40. Friction force is now it's going to be 0.1 times these two together is 100, is 10 Newton is friction. So situation is you have this system and you're pushing the system is 10 kilogram and you're pushing with 40 Newton, but the kinetic friction Fk is only 10 Newton. Of course, you got leftover force. That means acceleration that way, acceleration will be 40 minus 30, which is the case here. 40 minus 30 times ma. So 40 minus 10 over 10 kilogram, and that just becomes a 3 meter per second square. But this equation F1 minus Fk is equal to ma. It tells you if this will not change. See, if this is mu k Fn, and if it's 0.1, so 0.1, and Fn was mg times mg minus equals ma. So as long as this guy is greater than that, is going to slide. It's not going to come to a halt. Okay, so as long as F1 is greater than mu k mg, which in our example, in this example, is 10 Newton, acceleration will not be 0. Now, what happens if it starts to slide, picks up speed 2 meter per second, but you reduce the applied force to 10 Newton in this example, okay, which is mu k Fn. You reduce to this value. Okay, what will happen? Well, at that point you have you're applying 10 Newton, you're opposing 10 Newton, then means acceleration will be 0. So acceleration is 0. This whole thing is moving at 2 meter per second. So this is some instant t, okay? So it's a t1. T greater than t1, it will just continue to slide at that, okay? Continue to slide. Yes, this force and this force are balanced, so it will just continue to slide. Yes, at 2 meter per second. What if you say, okay, I'm sliding at, that's my system. I'm sliding at 2 meter per second, and used to be F1 because 10 Newton. I say, let go, F1 0. Well, that doesn't turn off this guy doesn't turn off Fk because it's just sliding. It turns Fk, it still is mu k Fn. Of course, same mg Fn, exactly same situations before. This is same equation of motion. It's the same equation of motion, except now this is not there. So the acceleration is so this is the x direction. So acceleration ax becomes minus mu k mg over m, and vx is 2 meter per second, and so this 0.1 times 10 is minus 1 meter per second squared. Is going at this, is decelerating at that. That means we'll come to a stop. At t equals to 2 seconds. That's how the whole dynamic will play out for this kind of situation. Now, one rule very fast, and maybe you want to go over this and a couple of times, make sure you understand every step I made. Now let's get back to this today's, I want to make some progress. I had set it up and I didn't do it yesterday, and I want to make some progress with this. Okay, this is a really important problem because there's so many features here. I don't know, maybe I should have some timer here. I forgot to keep the timer. Okay, so here's a string that goes over this pulley, and we are going to use what is called frictionless pulley, but it's very strange kind of pulley. There is no friction here when it rotates on the axle, but there is a infinite friction here. So when the string goes over there, it's always is in touch. The string is not slipping, okay? If it's slipping, then the motion of this guy and motion of this guy will be uncoupled. And make sure you understand that. I'm going to make it my face bigger, so I've explained that. Okay, so let me say it. Okay, so I'm going to say if it's if the string it can slide without rotating the wheel, then the motion of this block and this block and this block will be motion of this block and this block. This go up and down, and this moves the same amount, completely decoupled. Okay, so you don't want that. You don't want that. That's why this is a very important. That's a very important assumption. Okay, that's very important assumption. A lot of students don't realize that there's assumption underneath it, and sometimes problems are constructed to make this slip, and you got to be aware of that. So the no slipping. So it's not like no friction only at the axle. And we will have friction mass much later when we talk about rotation, etc. Because this will be rotating, and I don't want to be bothered with rotation at this stage of the learning. So we just say massless, frictionless. So no friction, no mass. What does this mean? This means whatever the tension is on this side is the same on this side. Tension on the one side is equal to the same as tension on two sides. Tension on two sides now if this is not the case, in the case. So when we talk about rotation, we're going to have different tensions. So T1 equals to T2 equals to T. So it's a practice to write this out when you when you initially doing a whole bunch of problems with strings, you write the just don't use TT. Once you get the habit of TT, your brain, when you come to actually different, you can do TT. I've seen so many people doing that. It's ridiculous, All right, so you have TT. Now no slipping. What is no slipping is doing? If this thing moves a distance delta d2, this thing will move the same delta d1. Delta d1 is equal to delta d2. What does it mean? The same amount of time in time delta t. Well, this just means that this one dimension was the speed. It's a speed. v1 is equal to v2. its acceleration 1 is acceleration 2. So you can use a same symbol for both of them. So if this is going with an acceleration this way, just the direction is different. Their magnitude is same, but direction is different. So this is acceleration that way. So if I were to use this same coordinate system like x and y, acceleration vector here will be 0 minus a. I'll keep this guy positive, so put negative sign over here, and acceleration vector over here will be a and 0, because this is positive, this side is positive. So the vector is not the same because the direction is different, but magnitude, as the magnitude is concerned, they're the same. All right, this is a very simple. Once you realize we have to set up an equation for this guy, I set up an equation for this guy. The tension, let's try to set a motion for M1. So here can be, say it's a not sliding. Say mass is not enough to slide. So the tension will always pull away towards, so these two masses are coupled. Tension is trying to pull it away towards the other mass, you know. So called tension. So the other one, obvious one, is M1G. And as a result, there's a normal. Let's call it N1. I'm going to use symbol N instead of Fn. Okay. If this is not sliding, if this was the case is not sliding, then this will have, there have to be static friction. So Fs, I don't know if it's maximum Fs. Okay. If Fs is max, then we should write mu s times n. All right. So now if you do this x and y, then it's a t minus Fs equals to not sliding. That means acceleration 0 is 0. And n minus m1g equal to 0. So these are the equations here. So static friction, whatever it is, matching the tension. And we don't know what tension is. Tension is going to be obtained from the other guy. So we have enough mass, but it's not sliding. No acceleration. A equals 0. So there will be tension here, and then it will be M1, M2G. There is no normal force here, okay? No frictional force here. There's nobody is touching it. So just these are two forces. So is the y-axis that way. So T minus M2G, T minus M2G equal to 0. So here we got the T, which we can plug in here, and we can figure out what the static friction is. And from let's see, so immediately you get T equals to M2G, and Fs equal to if I square T equals to M2G, and N equals to M1G. Now you keep adding. So case 2. Next, what you can do is keep more and more. You had this much, it didn't move, but if you put a little bit more, so it still doesn't move. But here is a little bit you put in and start to slide. This starts the motion. So it start to move. So up to here, no motion. So this up to here, let's call M1 0. At that point, anything more than, if M1 is any greater than M1 0, let's M0, let's call it 0. In greater M0, motion starts. So this is my like a max second put, so it will be if it will not start to move. This move means if I look at the this place, this will start to slide. So this is the mass 2 and mass 1 to slide. That means if M2 was greater than M0, we're talking about M1 here. I didn't change anything about M1. Did I make, this is M1. Yeah, and this is M2. Did I mix it up? Yeah, this is M2. So let's see. So this M2, this M2. If M2 is greater than M0, then start to slide, right? That means when M2, not this mass, but the other mass, the hanging mass, M2 was M0, Fs, this Fs on M1 must be max. So now Fs max will be mu s Fn. So at that point, we can write that. Okay, so in this case, if you work out the equation again, so now the equation again, so you work out here M1 Fs max, acceleration is still 0, not sliding, tension Fn, M1g. So here you can see tension is Fs max as before equals to mu s Fn, and Fn equals to M1g in here, minus M1g equals 0, which makes equal to 0, same thing. Together in here it gets mu s M1g, and this is M0, so this is M0g, and this is T now, so T equal to M0g. Now plug in here, together that's going to see M0g equals to mu s M1g, cancels out. So mu s must have been M0 over M1. So that's how we discovered what was the static friction thing. Okay, so case 3, final case, promise. Case 3 is M1 block starts to slide. Let M2 be some M2 prime. Okay, so these are all fixed. So now we work out, you are going to get for M2 prime, you are going to get M2 prime G, and you're going to get a tension. Okay, you're going to get tension, and acceleration 2 will be like that. So M2 prime G, you can see I can take this as a positive direction, which is, or you can take this as the positive direction. Let's keep the same as before. So t minus m2 prime g, this is going to be negative, so minus m2 prime a. That's what I was trying to avoid by picking the directions. So suppose I had taken this as the positive direction, then I'll get m2 prime g minus t equals m2 prime a. This same equation is just, sometimes I think like that, it's arbitrary. So, and this guy will be t, same value of t, this, because of our assumption, fn m1g. Now we have a fk, which can be safely said to be f mu k fn. So this guy is going to give me fn minus m1g equal to 0, and it's going with the axis in this way, so t minus mu k fn equals to m1a, and this one can be put in here, so m1g from here it can put in there, and this t is equal to m2 prime g minus a. It's not m1a here, not g, m1a, because this is the positive x-axis. Okay, so this t equals to m1 m1a plus mu k m1g. Let's keep this m2 prime g minus a. There's several ways of handling. You can get equate it and get done, but I'll show you solve for t and a. That is usually the problem in this case. So I would write this guy like this. I'll write in this form, and then you will see it's much easier to do the algebra. And I'll write this guy like that, t minus m1g mu k m1g is equal to m1a. Add this up, then t cancels out. Then m2 prime g minus mu k m1g equals m1 plus m2 prime g, a. So the a is immediately you get is m2 prime mu k m1 over m1 plus m2 prime. And obviously you can pick any of these, and say you pick this guy, get the t m2 prime g minus a, and you put this here, and you can get the tension m2 prime minus mu k m1 over m1 plus m2 prime. So there's a g somewhere missing, the g missing at the top. So this is the g. Of course, you bring it up here, you can simplify a little bit. So m2 prime g over m1 plus m2 prime, and you get a m1 plus m2 prime minus m2 prime plus mu k m1. And so this is m1 m2 prime over m1 plus m2 prime g times 1 plus mu k. I hope I've done the algebra right, because I didn't really do it earlier. And if there's algebra, you can just correct it. Okay. All right. So that's actually completes our discussion of this system, various scenarios in this system. I didn't pick up a particular problem to solve or a particular angle on my thought. I just want to make sure that you have tools to handle any problem that comes up like that. So we're going to do a lot more pulley problem. Like there is this pulley problem that very common to ask. So you will have something over here, and instead of flat, it's at angle. So they have inclined plane, but pulley is so here's M1, here's M2. Imagine this guy is going down like this, so this is kind of lifting like that. Okay, now learn to analyze this problem. Consider this to be frictionless, massless, no slip. So these three assumptions, assume these things. Try to solve this problem, because we already know how to handle something on an incline. We know how to handle this kind of stuff. We know how to handle this kind of stuff. You should be able to do this problem. All right, I think this video is a little bit long, and I'm going to stop it here and talk to you later.